opportunities of hybrid green and gray infrastructure. Um, Thank you, Anka, for recording the meeting. As I said, welcome to all of you. I hope you're going to enjoy the next 1.5 hour discussing these opportunities. Well, first let me introduce myself. My name is Frans van der Ven, working with Deltares as a strategic advisor on urban water management and with Delft University of Technology, but primarily here as trying to lead the vision and leadership team on hybrid green and gray infrastructure. And to tell a little more as an introduction to the meeting today, here's the group of people that is now working on this topic, hybrid green and gray infrastructure. I'm not going to mention all the names. All these contributions are very much acknowledged and valued by us. What is the objective of this meeting? Well, the objective of this meeting is to open the discussion on hybrid solutions, to demonstrate the opportunities, to show examples, and to lead by example, as Andrea Robini used to say it. But also to define the research gaps and other barriers that we are encountering in coming to hybrid solutions. So what we need is innovation and cooperation of experts and organizations to come up with hybrid solutions. This whole idea is based on a white paper we have recently submitted to the Bureau of Water Europe, a white paper on hybrid green-gray infrastructure, a white paper meant to inform, inspire, nudge, recommend the developments of hybrid solutions. So that brings me to the program of today. If we want to lead by example, we first have to tell you what we mean with hybrid green and gray. That's what I'm going to do in shortly. But then we're going to show 4 examples from Sweden, from France, from the Netherlands and Spain, and another example from the Netherlands. And we'll hope to finish with a discussion on the opportunities, barriers, and research needs. And of course, for all the participants, comments and questions are most welcome in the chat, so that we can use that in the further. The idea is to have a presentation of 10 minutes of each of the examples with a 5-minute Q&A. So there will be opportunities for questions regarding each presentation. Well, what is the background of the problem? The background is say, the gap we see between the nature-based water infrastructure community and the grey water technology community, as we called it. So people are working on either on nature-based solutions and infrastructure, and many people speak about the need for nature-based solutions, and rather than grey solutions, it is sometimes said. Whereas a lot of us, of our community, is working on grey water technology solutions. In that, and we see that these worlds are separated, and these pictures nicely illustrate the separation. That the green people working in the city, greening the city and making lively environments. The water technologists working in say water factories that far away from the city, no one knows what happens there. It's behind a fence, well protected, and that characterizes the two communities. The two communities is on one hand led by landscape architects, etc. Work in the city with very visible solutions, decentral, multifunctional solutions, opportunistic, whereas the engineer tries to perform better, optimize the performance of each solution. Facilities invisible behind gates, often monofunctional, cleaning wastewater, producing a specific type of wastewater if possible. Two different communities, and we think that the world could benefit from an integration of these two, an integration of green infrastructure with gray infrastructure, with the gray water technology solutions, but also with the smart solutions, with the water smart solutions, as is the topic of this Water Innovation Europe team, Water Smart Society. All this to define a more effective, attractive, and efficient way to deal with our water resources and to provide services to our community and to the ecology. And a couple of hybrid solutions, and we'll see more of that. The Puri drainage, the upper left corner, Stefan Janssen is going to talk about that. But okay, we will see more examples in the presentations, I would say. And our conclusion of the white paper was, well, we can do better. We can do better by optimizing the synergy between nature-based solutions, water technology, artificial intelligence, monitoring, control technique, and integrate that in one solution, rather than doing treatment trains. Even try to integrate that in one solution. However, this requires new roles for the existing players, for the utilities, for the water authorities, for all the others involved, for the spatial planners. It also requires learning by doing, because we have to experiment and to learn a lot from innovative solutions. It also requires new governance, new spatial arrangements. And to that end, it requires targeted research and development, targeted R&D, and that needs money, of course. If you want to talk about how to achieve this, well, we identified this according to the Symbiosis readiness level. Many people know the technology readiness level, but there's also a Symbiosis readiness level that identifies 4 characteristics, and that is technology, or the ecosystem, the network of cooperating organizations, the management, and the business character of the solution. So it's important to try to define these 4 components and to see stepwise from step 1 to step 9, as you can see in this sheet. Step 9 is commercialization, is the mainstreaming and the mainstream solution. Step 1 is the initial idea, how to come from one to the other in a very cooperative way by bringing people from the green community, the gray community, and the smart community together in and developing new solutions to this. What we are going to do today is not only to ask you to listen to the presentations and have a discussion on the opportunities, but we would like to know who is in the meeting. And to that end, we will ask you, for those that didn't do it, to fill in the survey form. Anka will post a link to the survey form in the chat shortly. So please, well, in the meantime, these are very simple questions, just who you are and what you think about and know about hybrid, to work on. And then after the presentations, we will have a post-presentation questionnaire, something like a Mentimeter-like survey that is used to steer the discussions in the panel. But okay, that will be for the next step. So for now, I thank you for this introduction, and I would like to give the word to Godeke to present the first example. Godeke Black and Anna-Maria Koolberg from Luleå University and the drinking water, or the water service of Sundsvall in northern Sweden have developed a specific solution. And may I, Godeke, may I give the floor to you to present the first case?
Yes, thank you. Definitely. Yes, here we go. And I think that you should see my
Top.
screen.
Thank you.
And yes, my name is Godeke Bleken. I work at Luleå University of Technology at the Urban Water Engineering Group, and work also in these two research centers, which are named down there, Dagonet, which is a Swedish research cluster, and Drisel, which is a center of excellence in stormwater management. And we work in these projects closely with different companies, industry, municipalities, among others, with this Mid-Sverige Vattenavfall, Mid-Sweden Water and Waste Management. And Anna Maria Kullberg from Mid-Sweden Water was supposed to join me, but obviously she had problems with Zoom and could not connect. So if she's not there, then I will just take this presentation, but that's fine. We have worked, what I want to present today is a field system where we investigate different aspects on the treatment of highway runoff using green-gray infrastructure. And this is the system, how it looks like, or part of the system. The bridge you see here is the motorway bridge of the European Road E4, which goes through whole Sweden from the south in Malmö to the Finnish border at the northernmost point of the Baltic Sea. And this bridge was built some years ago. And the runoff from this bridge deck is treated in this bioretention facility. And as a first pre-treatment step in this facility, we also have a concrete sedimentation, pre-sedimentation facility. And this is how it looks during dry weather, the facility, and during wet weather, you see that there's this water standing there, and the water infiltrates through the system and is treated by different processes in the filter material. And as I said, before it reaches this system, it passes through the pre-treatment facility, which is this gross pollutant trap. And this is a picture of the system from above. The stormwater enters here into the system, SW is the stormwater, and then we have this gross pollutant trap here. And then this water is discharged to these three bioretention cells, which are designed in different ways, with and without vegetation, or with different filter materials. And the design was done by our university together with this Mid-Sweden Water company, with Sundsvall municipality, and with the National Swedish Road Agency, who's responsible for all national roads in Sweden. So that was done jointly. So this is a quite good example for collaboration project where we from academia already came in early in the design process to gain as much as possible from the system and to use the opportunities which these systems provide. Why this facility? The polluted water from this motorway has to be treated before it's discharged to the receiving water body, which is a bay of the Botnian Sea, so the northern part of the Baltic Sea. There was no need for retention of high flows or flood protection, so it was mainly the water treatment, because the water from the bridge does not contribute to like high flows or flood risks downstream, because it goes directly to the sea there. And the catchment is about 8 hectare, and it's 4.7 hectare impervious area, and that is mainly the road area and a motorway exit. In total, the system was quite expensive. That was nearly 1 million euro. However, that was not due to the system only. There was also because the soil on site was a contaminated soil. So there had to be done some measures, and that was a major share of this total cost. So that's why this is really expensive. But the system itself was cheaper. But this is one of the slides which Anna Maria was supposed to. I cannot tell you exactly how much the system itself was. The system was financed by the Swedish Road Agency when they built the bridge, because they own and operate the bridge. But then they have a contract with this Mid-Sweden Water company, and they are responsible for the maintenance and operation of the system. They remove they maintain the pre-treatment system, cut the grass, and do inspection of the facility. And that was built about 4 years ago, the system. We have done several research projects, or not, we are currently doing a range of research projects connected to this facility. We look, for example, on different pollutants. We know that these systems work quite well when it comes to most of total metals and so on. Phosphorus also in this case here, total suspended solids. But we look on also on other pollutants. Microplastics is something which is a bit in right now. So we've looked at microplastics, have a paper under review on that. We look on a range of organic pollutants, and then we also go a bit more into detail. For example, here, as I showed here, when it comes to metals, we do not just look on total and dissolved metals, but we also look on the fractionation or partitioning between, for example, colloidal and truly dissolved metals. And that is quite interesting because it gives us much more information about the metal treatment, the treatment processes. And that is also connected to, for example, the Swedish environmental quality criteria, which are connected to the European Water Framework Directive, because there they define values, for example, for bioavailable metals and discharge or like target or guideline values for bioavailable metals. And we cannot say, or it's not enough if we simply look on total metals, but we also need the more information here on these other fractions. And what we also do is looking on like how the performance varies between different rains, but also within the rain. Partly we have quite high first flush events out of the filter. And so these are topics which are quite interesting. Another point which I didn't, or which I forgot to put on this slide, is that we also have the opportunity to, I go back here, to measure the stormwater quality, and then after the pre-treatment step, and then after the filter section. So we can basically look on this treatment train and see the different steps. We cannot just look on the system as a big system, but also quantify the contribution of these different treatment steps. So that is the research we are doing. Then I want to come to this, and there was this Symbiosis readiness level. And here I must admit that I first had to read what SLR is. And I hope that I understood that. If not, sorry for that. But when I looked on this table here, like where we are, then in general, these bioretention systems, I would say, are on a relatively high level. We know that they, in general, perform well, that they can treat, for example, total metals well, that they have a potential to, function. We know how they should be maintained and so on. So in general, I would say that is an established technology. However, when it comes to, for example, many organic pollutants, to specific pollutants of emerging concern, microplastics and so on, there we still face many questions, and there we really need to learn more. Because what is important is that these systems are relatively, or I take it the other way around. I was on a meeting some time ago, and there it was said that we work with low-tech facilities when we talk on nature-based solutions. But these nature-based solutions are no low-tech facilities, but they are very complex facilities because they involve many different design features, like different filter materials, inflow, overflow, vegetation, and so on. So we have many different like biogeochemical processes, we have varying ambient conditions, we have different designs, and so on and so on. And I think while we know these systems relatively well as a black box, we have to know more about understanding this complexity and see how, as I said, these different design features, ambient conditions work, how different pollutants of emerging concern are treated. And another thing which I think is very important here is that we also look more on field and long-term tests, because there are many studies which have been done in lab, in small scale and short-term studies. But it's very important that we understand how these systems really work in reality, how we get out the results from our lab work into field, how they perform in practice. And we've done some work on that. And unfortunately, sometimes it is a bit depressing when you see how these facilities work in field. So they do not work automatically or per se, but we have to really see that we design them correctly. And I think sometimes there is a misunderstanding when we look on projects in reality, implementation projects, that there is some kind of assumption that if we build blue-green infrastructure, nature-based solutions, they will be sustainable per se. They will work automatically. They will definitely treat the water. But we have examples for example, bioretention facilities, also green roofs and other such facilities, where it would be better for the environment if these facilities would not be present, which is a pity. So we really have to think about that. And the last point I want to come to is the multifunctionality. That is also connected to that, because there's a huge potential for multifunctionality in these nature-based or blue-green solutions. But there can also be conflicts of interest. And understanding these, investigating these, and not just ignoring these, that is also one thing which I think is really important. And also to get in different disciplines working together. That is one thing which is important. And the last point, I also think that we need more thorough sustainability analyses, because these systems are not sustainable per se. There are some facilities which, to be honest, are rather kind of greenwashing than really sustainable. We have done some sustainability assessments of such bioretention facilities in Sweden, and some are quite bad because they use a lot of concrete in these, for example, need a lot of energy to construct them. That is not sustainable. Okay. That was what I wanted to say. Thanks for listeing.
Oh,
and yeah, best regards from Anna Maria. Sorry that she couldn't come.
A pity she could not connect, indeed. Huh? That a couple of minutes for some questions. I did not see any questions in the chat so far. Is that my mistake, Anka, or is that?
No, there aren't any questions yet.
I do have a question, however, Gotike, and that is, what can you tell about the performance in winter?
I didn't hear your question.
Sorry, what can you tell us about the performance of this facility in the winter period?
Yes, that is also one thing which is interesting. In general, it works relatively well. The thing is that in this north, or it's quite far north, this facility, we have relatively long periods with temperatures below zero, and then we don't have any runoff into the system, and then it melts, and then the system starts again working. That in general, it seems as it works also during winter. However, it just when it starts melting, then we can have some problems because there may be like ice in the system which has to melt first. So we may get some more overflow in this period. But also, let's say in southern Sweden or like parts of continental Europe, northern Europe, we also have winter conditions where these systems may work differently, or where we have issues, for example, connected to road salt. That is one issue which we have investigated a bit, but there is some knowledge about that, but also there we need more knowledge. But this is a good example what I meant with these like varying ambient conditions, because we cannot just design systems, for example, for let's say the Netherlands, and then assume that we just can copy paste the design and that it works in northern Sweden and southern Spain. We have to adapt them.
That's why the next example will be from France.
Yeah, there are different questions in the chat, but
yeah, in the meantime, so let's to come back to the questions in the chat. Quite simple. We will record the chat, and I'm asking Gotike to reply to each of you who asked the question individually. That could be done afterwards. Gotike, if you can agree with that.
Absolutely.
I would like to continue to the next presentation.
Okay, thank you.
Thanks for the contribution. I think, and thanks Anna Maria as well. I hope she's listening. And despite the ban for Zoom in the municipality, unfortunately. Edouard, welcome.
Thank you.
Just in time. Well, the others didn't notice, but you just came in. And we're going to change climate from northern Sweden to France. The Pacheco envelope factory, I understood. Edouard is working for Uver. Will you introduce yourself and could you limit yourself to that 10-minute presentation, Edouard?
Yes, I can do it. So I start now. My name is Edouard Cellier, and I work in a company called Pocheco. I think you can see my screen now, on which one I present the company. Well, Pocheco is paper envelopes producing company. We've been doing that for the last century, since 1928, and we produce up to 2 billion envelopes per year. And this is our plant, actually, from which one I'm talking right now. As the Intergovernmental Panel on Climate Change, the IPCC, tells us that resources are running out, for the last 25 years in this company, we changed all our old 20th century habits to new habits more respectful of our environment and its biodiversity. And the water topic was a huge one for our industry, and I will explain why in the next few minutes. We developed in this plant a way of working we call ecolonomy. Ecolonomy is a contraction of two French words, which mean economy, which actually means in English save money, and ecology, which means ecology, just like in French and English, are the same. We started to develop this new method of working, which permits us to save money while taking care of the environment. When we looked 25 years ago from now on the working conditions in our factory. It started in 1997. The company was not doing that great. We had some issues related to the quality of our envelopes. Some customers got unsatisfied, and the board of the company decided to renew the boss of the plant, and a new boss came. His name is Emmanuel Druon, and he is still here today. And indeed, when this person arrives, he finds some serious issues in the plant. He realizes that in the teams, you had some harassment, moral harassment, sexual harassment. People were not quite friendly, the one with the others. There was some financial misguidance from the previous leading team of the company. And above all of that, obviously, the ecology, the environment was clearly not a concern for the team that was there before this new boss, Emmanuel Druon. So the first task this new boss and its new team decided to work on when they entered into the company was to improve the working conditions. We couldn't harm ourselves while working. And the first thing we did to engage on this topic was to remove all the hazardous materials we use to produce our envelopes. And one of those hazardous materials was the ink. This ink we use to print the logotype of our clients on our envelopes. They contain some solvents, some heavy metals, they bring to the atmosphere some organic volatile compounds, and so on. So whenever we had to deal with those inks to handle them, we harmed ourselves as operators in the company. Emmanuel Druon, the new boss of the plant, knew he couldn't work alone on the renewal of the company. He had to get mobilization of a large part of the team. So the first year of his arrival, the first year after he arrived, he and his team worked hard on making everyone a real actor of its own job. We made the operators in our plant write down and share the way they worked, their procedures, talk about it with the different teams of the workshop, and in the end, everybody realized that they had control over their work. This permitted our colleagues to develop new ways of working, to develop some technical improvements on the processes, and so on. And then came the ink topic I talked to you just a few minutes ago. To handle the ink topic, Emmanuel Druon, the new boss, asked the team, is there something non-hazardous we could use to print on our envelopes? Someone in the company said, of course there is, but it's going to be way more expensive. And Emmanuel Druon answered something like, okay, more expensive, can you explain? Well, it's going to be more expensive. The cost will be way higher. And so they keep talking about it. And Emmanuel Druon says, okay, the cost will be higher. The price will be higher. I understand, but what's the cost for the environment? What's the cost for the working conditions for our health as operators of this company? And the idea was to put on the same level of priority the health impact of the raw material we use, the cost of this raw material, the ink, and of course, its environmental impact. And this is when we decided to do that, to redefine the priorities of the company, we ended up working together with our ink producer on the ink's recipe. Ingredient by ingredient, we simplified the recipe of this raw material to make it non-toxic for the health of our colleagues. And automatically, if it's not toxic for the health of our colleagues, it's not anymore for the planet. And having simplified the recipe, we've made some financial savings. In the end, we saved money on the cost of our ink because it was much more simpler raw material. The composition of the raw material was way more simpler than the old one. But we didn't stop there. And when we received those new inks, we received them in
3 minutes, Edouard?
Yes, I know. I'm going faster now. When we received those new inks, we received them in 1 cubic meter water tanks. And in those 1 cubic meter tanks, you had a little bit of pigments and a lot of water. So what we decided to do was to buy only smaller barrels of inks, which are the ones on the picture now. It's around 200 liters barrels, and there is only the pigment in it, and we dilute the pigment ourselves in order to make the ink. So we save money on the transportation and CO2 on the transportation. But we didn't stop there. The idea is that when we end up a production of envelope, we need to clean the machines with water. And these machines, they are dirty because of ink mainly. So when we use the toxic inks 20 years from now, the wastewater we ended up with was toxic, and we had to send it away in a wastewater treatment plant, which costed us 40,000 euros per year. Now our inks are not toxic anymore. We realized we could treat them naturally thanks to a green infrastructure you have on the screen now. It's simple. It's quite simple. It's just 4 different kinds of bamboos in which are able to treat non-toxic wastewater. And this permits us to save 40,000 euros per year. The cost of this infrastructure was 150,000 euros. So we have a 4-year payback. And this is the next step, the last step. When 10 years after installing the bamboos, we worked on our building and we started to redo the roof. And we developed a green roof, which was quite interesting for us because it permitted us to harvest the rainwater quite easily. And now we are on a closed loop on water in Pocheco because we harvest the rainwater coming from the green roof, use it to make our inks and to wash our machines. And then this wastewater we get is cleaned by the bamboo's wastewater treatment plant. And every 4 years, we cut the bamboos and we heat ourselves thanks to our biomass heater. So in the end, if you do the water cycle of our company, we can say we heat ourselves with rainwater. And so regarding, just to end this presentation, regarding the SRL level, I think we are about not so far from a 9, because this is a commercialized offer we have used there. And we have proven the money savings and the sustainability interests too. And regarding the smart part of this infrastructure, I think it's more about not that much about technology, but maybe more about how we manage to make this wastewater treatment plant a central key to the whole processes of the plant, from the raw material, which is the ink, to the building with the roof. Okay, I think it's 10 minutes now.
Yeah.
I hope it was not too fast.
Well, thank you. I think it's a wonderful example, Edouard, of something that is discussed over this week in the meetings very much, and that is engagement. The word engagement, yes. And what I've seen in your example is that the employees of the company are deeply engaged in developing this plan and coming up with own ideas about new solutions and bringing this further. There's a very long question in the chat I see from Clemens. We'll handle that later because of time. But it's could you briefly elaborate on the barriers that because I can imagine that you spoke with this development about much positivism. But I can imagine that there was a lot of barriers as well.
There might be, yes. The first one was the regulatory one. We had to deal with the French authorities, the French environment minister, which asked us to do a lot of control in the first years. So every week we had to control the quality of the water, because the wastewater coming from these bamboos goes to the municipal, the public wastewater treatment plant, because the quality is good enough to go there. So we had to control a lot, and for many years before they started to trust the system and tell us, okay, once a month or once every 2 months should be enough for us. We trust the system. And the other part is that the other barrier maybe is in the individual compartment. You need to make sure everything going into your company, your industry, is how can I say, eco-friendly, I don't know, but will not harm the bamboos, because everything goes back into the bamboo. So you have to pay a very good attention to everything that is coming into your processes, your industrial processes. This was the biggest part of the job with this installation.
A final brief question. You say the Symbiosis readiness level is 9, which is commercialization. Is Pacheco selling this solution to other similar organizations?
No, we're not. We use the commercialized offer from a company which doesn't exist anymore. But today some other companies do it too. And as Pacheco, we work together with other companies, other industrial, to help them in the process of implementing this kind of solutions.
Yeah. Well, thank you, Edouard, for the introduction. And of course, there's a couple of questions that
thank you, Frans.
Later on. This was a very typical example, like the other typical examples we have to present today, one from the industry. We now move through to an example that is the reason why the Dutch soccer players are so performing so well at our championship, as you all know. Because it all starts in the castle, and the castle is the football stadium from the Spartak football team in Rotterdam. and that's where Joshua Gallegos developed the irrigation system for the fields. And I think, Josh, it's not the only subject that you're talking about, but definitely the reason why the Dutch are doing so well.
Might have something to do with it, huh?
Joshua, the floor is yours.
Thank you, Franz. Just bringing up my PowerPoint here. You have the full screen?
Yep. That's to say, it's not a very wide screen, but we can read what's in there. I can read.
It's not a very wide screen.
I don't have it full scale.
Maybe I can do one quick adjustment here. I have two monitors and it's constantly a fight with Zoom. So I'm taking one of them out. That should be better, huh?
There you are. There you are.
Okay, good afternoon, everybody. And again, my name is Josh Gallegos, and am working with TU Delft and Field Factors, which is a technology provider for the concept that I'm going to discuss today. The concept is called the urban water buffer, and also in other ways we use the term blue block circular water systems, and the purpose is making rainwater into a resource. So really valorizing large quantities of rainwater. And today I'm going to talk about two cases, one of which is in Holland and one of which is in Spain. The first case that you can see on my screen now is located in the city of Rotterdam, and this is the one Franz was referring to. The concept here in the first full-scale pilot was applied to provide water to the soccer stadium. And what we do is combine rainwater harvesting, biofiltration, and aquifer storage, treatment, and recovery to essentially shift water from wet periods of the year to dry periods of the year. And that happens through 5 steps. The first step is generally collecting water from surfaces, like rainwater harvesting is broadly applied. Second step is to retain that collected water in a retention tank, which is typically an engineered construction. I'll show you a few examples of later. And the third step is to filter that water using a biofiltration system that's installed in the urban environment and also has aesthetic benefits as well. After that, we infiltrate the water into the deep aquifer where we're able to store very large quantities. And in this example, it was about 15,000 cubic meters of water recovered a year. Two cases that came on this year. We just finished commissioning a urban water buffer here in Kroonvliet Park in the Netherlands, in The Hague, that is. This was a city block scale installation. So you can see the pre-construction on the left side here. It's a large park with community gardens there. A major renovation was done, and part of that was to disconnect this pink area that you see on my right side of the screen here from the existing drainage system that feeds to the municipal sewer, and turn it into a collection ring to supply these community gardens and actually an urban animal farm that's located at Kroonvliet Park. In the background, you can see finished urban water buffer in the foreground, or biofilter rather, in the foreground. In the background, you can see the urban gardens. But on the right side, I think a very nice picture of this blue ring, which collects rainwater from all of this area that I showed you in the last slide and channels it to a central buffer installation here in the center of the park. From there, it goes to the biofilter you see on the left side of the screen, and then by gravity flows into an infiltration well that my pointer should be indicating now, where it gets down to the aquifer and can be abstracted later using conventional means for use. One technology applied here was the water shell Atlantis. This is the buffer system. So this is it's a hollow body that has plastic skeleton inside to hold water. That's the initial collection. And the Blue Blocks biofiltration system with the aerating distributors here on the bottom. The system here is estimated to collect about 40,000 cubes per year for use at the park. The investment, not including the drainage retrofit, so including technical installations, biofiltration, buffer, was about 300K. And operations and maintenance is estimated at about 10 a year, and most of that is having to do with monitoring water quality there. So we're still doing a lot of research as well on the performance in that way. The city of The Hague mentioned the major driver for selecting this solution was that they're looking for solutions that address multiple issues, and the urban water addresses flood risk, the supply of water, and also through that supply of green areas, urban cooling as well. The second case that I'm going to present here, we go down now to Madrid, and these are the Cuatro Torres, or the 4 towers located. I think they're the only 4 skyscrapers in Madrid. And there was also a major renovation project going on here with this black tower you see being built. Part of that was the construction of a municipal park, quite a vast area, as you can see in that picture. And within that park, you have multiple terraces and a large architectural water feature at the bottom. So the application here was to collect rainwater to feed, to supply that architectural water feature, and also to provide a sort of ongoing treatment to remove, in particular, nutrients from that. And in this case, there were what they call zanadas drenantes, or filter drains, installed on each of the terraces. So through the whole park, the water is collected in these filter drains, which is a geomembrane filled with conglomerate you can see in the picture, and a pipe at the bottom which channels all the water to the bottom level of the park, where we also installed a subterranean buffer, much smaller in this case. And then that water goes through the Blue Blocks biofilter to get pre-treatment before entering the pond. Additionally, this pond water is cycled through the filter when it has sufficient water in it to maintain that water quality there. In this case, we are looking at a much lower recovery. Of course, this is in semi-arid climate of Spain. And we dimensioned the system according to that to be quite a bit smaller. The investment was about 120K, and again, O&M were on the level of about 10,000, and mostly it has to do with just needing to take consistent water quality samples and try to quantify performance on a number of aspects that the authorities in Madrid are interested to find out more about. So there's a number of things that are being piloted, of course, like in many cities in Madrid, to address the issue of water shortage. And in this case, more than just providing good water quality for the pond, we are also trying to prove Blue Blocks as a feasible solution for the pre-treatment of rainwater for urban managed aquifer recharge, or the full 5-step process that I presented in the first slide there. When we move to this idea of symbiosis readiness level, I guess from the rubric provided by Sommer that you showed earlier, Franz, I think we're also somewhere around a level 7, and that's based on really specifically from that chart. We have a large group of partners who are interested in the concept from different disciplines. We have demonstrators now in place, and more coming. There's a lot happening with field factors, especially in the Netherlands right now, but other places as well. And we have monitoring underway for these systems, but there are, of course, a lot of issues that are still outstanding, and several of them you've touched on already, and Gotika as well. The organizational arrangement for management, we run into a number of ownership issues. Maybe the municipality owns the filter, but the water company owns the water, and there's a sort of a gap about who actually can maintain a system when nobody owns the whole thing, and who has the, frankly, who has the capacity to maintain the system in terms of understanding how it works. That's one thing we've been dealing with a lot. Moving to the business side, it is still expensive when you're basing your return on investment on the savings of purchasing municipal water, which is very cheap, even in Madrid. And we think that establishing a value or taking an angle that quantifies the value of water security. So what is water worth when you don't have it? Sort of as an insurance approach, which makes a lot of sense in terms of coming to some realistic numbers about what this water that we're providing is worth. And finally, on the technical side, more the area that I'm working directly on now, there's a lot to be done in terms of optimizing treatment performance. So as Gotika again mentioned at the first talk, there are a lot of very promising numbers associated with biofiltration and with properly installed and managed systems, but it's very easy to turn those numbers upside down when they're not managed in that way. And so that's something that not only needs to be executed and runs into these issues of organizational responsibility, but also it needs to be communicated clearly throughout the course of the project, especially after delivery, where people are sort of thinking that we bought this thing, it's installed, and now it's there, and now that we don't have to think about it anymore. That's just not the case. So there's a few other topics here maybe we can continue to speak upon, but that's what I had for.
Right.
Yeah. Thanks very much.
Okay, so I'm sorry. I thought you were going to conclude the presentation. There was a question in the chat. One of the questions in the chat, Josh, that are you using first flush in these systems? Is that are you using that?
First flush avoidance.
Yeah, I suppose so. That is meant.
Yeah, and this is the first one in the Rotterdam installation did have a sewage implementation where the initial water would not enter the buffer tank, and that is something we think about. We're also elaborating, as I showed with the drainage ditches, various other pre-treatments that we can bring in. I think one thing that's interesting to observe is when you get super local with the collection and you really are not allowing it to move through a lot of surface before you collect it, you see much lower numbers in terms of a lot of pollutants than are regularly reported in literature. So that's been a win for us already. And from there, we're looking at first how to optimize the removal of the most common pollutants that you see in stormwater.
Mm-hmm. Well, and then another question by Dominique Gattel summarized that of course you have a natural filtration system. Do you renew this filtration system every so many times? And how do you dispose of the biomass that comes out of the biofilter?
So the replacement of the filter media is definitely an issue. It turns out that with the structure that we have, the biomass, the plants themselves are doing a lesser, let's say, quantity of the removal than the filter and the physical removal absorption in these processes. But there is ongoing work to develop this, clearing, replanting, and in terms of replacing the media itself, it seems like it can be quite a long time, on the order of 5 or 10 years. again, very site specific, depending on how much, phosphorus is coming in at a certain location.
Well, thank you, Josh. Thank you for the presentation. And I would like to move on to example number 4, which is not so much an operational technique, but more of a, say, research into a solution strategy that could be operational, that could be used to say in integrating blue, green, gray technology. The Puri drain as an example for expanding a drainage system with robust water technology to remove nitrogen and phosphorus. A research project more in the rural area, but Stefan Janssen knows all about this, and he's going to explain that to us. And maybe this is interesting to a technique to be integrated in our nature-based solutions in one way or the other. But that's the big question. Stefan, go ahead.
Yeah, thank you very much, Frans, for introducing me. I think what I will tell has some nice links with what Joshua showed. The interesting thing is that he showed a nice example for a more urban environment, and I will show quite a similar philosophy actually for a more agricultural system. And we call it Puri drain, which is a combination of purification and drainage, which makes sense, of course. And the idea was to expand the agricultural drainage system with robust water technology to remove nitrogen and phosphorus. But before I will go into the examples, I will take one step back. Why we did what we did? Well, the main incentive was water quality issues. As most of you know, nutrients form a major challenge there. Water Framework Directive sets very ambitious goals for nitrogen and phosphorus, and river basin management plans actually mention that measures have to be taken. And one of the examples of outcomes of eutrophication is, of course, toxic algal blooms, which the picture shows. Well, if you look at the Netherlands, one of the most persistent sources of nitrogen and phosphorus is diffuse emission from agricultural soils, which makes it very difficult because point sources are more easy to tackle. And how can you tackle diffuse sources? And one of the other problems is that even if we drastically reduce NMP use right now, these diffuse emissions would go on for years. So we need a solution for this. And our idea was to look into the drainage cycle, which is already there. In the Netherlands, about half of the Dutch agricultural soil is drained. And this creates actually a sort of a natural reactor system that you could use to treat the water. So our idea was to see how we can fit in water treatment systems into this drainage cycle. And well, I will show two examples, one for phosphorus and the other for nitrogen. For phosphorus removal, you need some form of chemical treatment. And we chose for chemical immobilization using iron oxide coated sand. And this is a very nice material because it's a side project of drinking water production from groundwater. So the groundwater from drinking water is put over a sand filter to remove iron and other particles. And then iron-coated sand is formed. And it's low cost. It has a very strong phosphate binding, good permeability, and very limited side effects. So it's a very useful material. And with this material, we did some field tests in the flower bulb area. And it's a very nice region in the Netherlands where a couple of months ago, you could see very nice, colorful flowers. But there's a high amount of phosphorus in the groundwater there. So we need treatment. And we did a very nice project together with a lot of parties, including the Water Authority, farmers, several research organizations, constructors. Well, that was very nice. And we tested 3 forms of treatment. The first one is to put the drainage tubes into a bed of iron oxide coated sand, like in the left side picture. The second one is to move away a little bit from the drainage in the soil and tackle the phosphorus at the point where the drains emit into the ditches by way of riverbank filtration. And the third option was to install the reactor, over which ditch water was filtrated. Well, I will not go into the details too much, but I can tell that all of the 3 options did quite well in removing phosphorus. About 80 to 90% removal rates could be achieved. But especially the third option had some clogging issues, which makes sense if you try to treat ditch water, which contains a lot of particles. But especially the first 2 options are quite interesting, because they, the drainage water is already gone through the sand filter, so to say, and it can be treated quite easily. And one of the advantages for the farmer is that it does not require land or other changes of his agricultural practice. So that makes it interesting for the farmers. Well, if you want to know more about this type of technique, there's also a couple of research papers out, which give more details. And well, I already mentioned some of the outcomes. Well, phosphorus removal rate could be achieved quite high. And well, costs of maintenance and maximum lifetime change, of course, as you can imagine, for the different types of practical working. And well, apart from the technical and scientific results, I think the main challenges are more in other fields, including practical applicability. The farmers, they don't want to have large areas of the land being used for other things. So you have to find space. That's a very important issue. The farms also don't want any obstruction of the drainage, because if a lot of rainfall is present, then the plants really should not be exposed to too high water levels. Another issue is the cost. Although these systems are not too high cost, it's always a challenge to find out who wants to pay for this. And well, in this project, we saw that it is always good to have both the water authority and the farmers involved, because they, well, my idea is that if you have the 2 parties both willing to use such a method, then you have some way of doing it. And very important, that's why we like this practical project. You have to gain experience to make people believe in such a method, and also, well, if you can take people into the field and show it to them, it works best. Well, that's also why we were really happy that we could scale up these options to a larger scale. So in 2018, 2 systems were installed at a farm scale of 7 and 12 hectare. And again, here there was this close cooperation between the different parties involved. And well, right now we are learning from these cases to find out more how it is behaving, and also to find out what form of structure works best. Well, very briefly, I will touch upon also another form.
Briefly.
Yeah, nitrogen removal. It's actually a very similar way. It's also trying to find a method of removing it. And for nitrogen, you can use biological removal, either using wood chips around the drains or in bioreactors, or using ethanol in reactors. We did similar experiments there, and well, similar findings. And well, to come to the final conclusions. So what we saw in this project, we could achieve high removal potential for NMP with little to no interference with agricultural practice, which is high benefit if you talk with farmers. And also what is very interesting is that you can use low-cost materials and very robust technology, which is important if you want to do this in an agricultural setting. In terms of the technological readiness level, I assess that we are around level 6, so in the demonstration level. So it's not yet in really commercial level, but well, we mainly are now facing the challenge of really well, convincing parties that this is really a system that could be used in practice. And well, that's also where the challenges are. So practical application, acceptance, cost, and also side effects. And I think what is really essential is first practical demonstration. You really have to do it together with partners. And one final aspect is that you have to look for the incentives. So we saw that these technologies had a lot of support, and there was a lot of interest in Water Framework Directive measures. So that helps. The other interesting thing here is that we found out that the farmers in the flower bulb area, they were willing to invest themselves if they could apply more organic matter to the field. And I think that may give some inspiration for alternatives instead of only legislation or financial incentives. That maybe you have to ask the clients what is important for them and why they would like to install such a system. So thank you. Maybe there are some questions.
Oh, thank you, Stefan. Indeed, we have one question from Jan Hofman, who asks what will be done with the iron-coated sand after use when it is fully loaded with phosphorus. It's sort of the same question that Joshua was asked about the replacement of the filter material.
Yes, yeah. Well, one question that the people are often asking is if we can reuse the phosphorus. Unfortunately, that's quite difficult because the phosphorus is trapped really firmly. But then a lot of farmers, if they apply new drainage, they often keep the drainage system in the soil. That can be done here because it's not it has no harm. If you would choose for a system in the left bottom picture here, the riverbank system, then you can take out the iron-coated sand, and then you could use it for other uses like construction or different things.
Okay, for construction purposes,
yeah,
basically. Yeah. You think that is safe for that? And of course, this whole story was about rural areas and say manipulating water quality, so to say, which is relevant both to the urban area as well. But how do you see this transferred to the urban environment, Stefan?
It could very well also be applied to the urban environment because principles are more or less the same. The key, well, I think two key aspects are what are the key pollutants that you want to remove, because that determines what kind of treatment you have to install. And the second one is what is the characteristics of the water quantity that you have to get rid of, because that determines the size of the system. Mm-hmm. But I think if you go to an urban system, then I've spoken to Joshua before about it, then you actually come to very similar systems like Joshua described.
Mm-hmm. That I can imagine. On the other hand, I think talking about hybrid solutions in the sense that we've been speaking about it, I think your solutions could still use a landscape architect, don't they?
Yes. Yeah. Now they're still a bit ugly, but if you could actually make them more looking more green and looking more nicely, that would be excellent. I totally agree. Yeah.
To integrate your solution in a
Yes.
better way in the landscape.
Yeah.
I think
Well, actually, I spoke with a colleague who always likes to think of also having an artist being involved too. But also landscape architects could be sort of the same, but to make something beautiful that people like out of it, that could be interesting.
I see one final question from Peter Rubik. He is asking a question that I did not quite understand. Is chlorine maybe a topic there?
Chlorine, we have not. Well, maybe this person can ask it himself, but
Yeah,
we have not have issues with chlorine.
No. If not, we know where to contact Peter.
Yes, yeah. If there are any questions, please contact me. Yeah.
Well, if you stop sharing your screen,
yes.
Stefan, maybe it's now time to. We have 15 minutes left for the discussion, and we prepared some questions for you in some sort of a Mentimeter setting, but. I'm a non-technologist, so I have to leave this to Anka and to Victor. Anka, will you switch up these questions and inform the people on how to answer the questions?
Of course. So I will launch now the first question.
Please do.
You simply choose the most appropriate for you answer. After that, I will share the results with everybody so everybody sees.
Hans, perhaps we can introduce it a little bit. We've put up this questionnaire for all the participants here in this webinar. One, to create some interaction with the panelists. And other one is also for us to assess information, because the visionary leadership team of Hybrid Grey and Green Solutions is really aiming at how can we contribute to the acceleration of hybrid grey and green infrastructures. So it's about collecting some information from you, the participants. We'll also, we go through the questions. These are 7 questions, I think. And then we try to get some response from the panelists after that.
Yeah.
So the first question would be, what do you consider not to be a hybrid grey or green infrastructure? This could be a wastewater treatment train, a rain garden with integrated piping, or a wooden structure as a floating island with plants and soil medium to treat the water. Or you could consider all of these as hybrid grey and green infrastructures. Please put in your votes. How does it work, Anka? Do you get the answers?
Yes, we have 27 votes by now. Let me know when I can end it. Share the results for a few seconds.
Okay, a few seconds left, people. Please give us your answers.
29 attendees responded.
We have 55 participants, so maybe I'd like to encourage the other ones to make a selection as well.
Where are you now, Anka?
31.
Let's go for the answer.
Let's show it, yeah.
Next question, more answers.
I think we get the answers first.
Yeah.
So these are the answers. You see 59%.
Okay.
Thanks. We might come back to that later on.
Sure.
Next question, Anka.
They are both.
There is a double question. Huh?
Yeah, it's a double question. It's about the presented examples of the 4 presenters. They did an excellent job, by the way. Very clear presentations and very nice solutions. So which of the 4 presented examples today do you find most suited as widely applicable? So if you look at your own situation where you live, do you think one of these solutions is best suited or best has a high potential to be implemented over there? So the ones are in the same order, the one from Godecke, the treatment train for road runoff, the water smart industry from Eduard, and the urban rainwater reuse from Joshua, and the period drain from Stefan. And the second sub-question is, how did you make this judgment? Is this based on that the solution has the highest potential to make an environmental impact, or that the solution has the least technical knowledge gaps, which you think, or the solution has the least barriers for uptake in policies and legislation, I'm sorry, and does the solution has or is close to a clear business case? Please put in your answers. Where are we about, Anka?
We are at 23, but 24, but it's growing because being double, it takes more time. So let's.
Next question.
Double question.
Oh, we have smart people here in the webinar.
A hard time. Huh?
Maybe you can sing a song meanwhile.
Yeah.
Where are we now, Anka?
27.
27. Let's try to get to 30.
Yeah, come on.
If you reach 30, just give a shout, Anka.
28. So we are getting closer. 29. So one more, and I will.
Who's willing? One volunteer.
Yes.
Yes.
30. Good.
Okay.
So and then share results.
Wow, nice.
Hey.
Very close to each other.
Yeah.
And then the highest potential to make environmental impact is one of the criteria to make this decision on. Very interesting. Thank you. Next question, Anka. And now, yes, now we go a little bit more focusing at the individual presentations or the individual solutions, I'd say. So if you look at the Sundsvall's road water runoff treatment train, what would be the priority action to make this widely applicable? So a little bit in other words, if you want to implement this in your own surroundings where you live, what would be the first action to take to make that possible? That is one, strengthening the EU policies and the legislation, local legislation for hybrid solutions. Or would it be that we still have to close some technical knowledge gaps? Or is it about demonstrating the economic viability and for a positive business case? Or is it you should better highlight the additional values for various stakeholders? I'm seeing time is running, and so I hope to do all the questions and get one or two feedbacks from the presenters. Anka, enlighten us. Wow. So the economic viability is here the highest, closely followed by various stakeholders and the policies. Thank you. Okay, we first go to the others.
Yeah, Pacheco. So the answers to the next questions are now all the same. The four different arguments that could be.
Yeah, and now we're focusing at presentation of Eduard on the Pacheco, the water smart industry, you know, with the ink and the envelopes? Do we need to strengthen EU policies and legislation to get it implemented? Closing some more technological gaps? Or do we need to better demonstrate the economic viability and create a positive business case? Or is it that we better highlight the additional values for various stakeholders? Interesting information, Frans.
Okay, whatever. And again.
Here, the economic viability is much more distinct from the others.
So let's move to the third one,
Yes.
to Josh's rainwater reuse solutions, not only in Rotterdam, by the way, but also in The Hague in Spain. And
Yes.
yeah, they all agree on.
Yes. Also, I think we have very few people saying there's technology knowledge gap left.
Yeah, yeah.
That's very nice.
And the final one is on the Puri drain.
Yes, Stefan, his presentation.
I can later tell to the partners what you think they have to do.
Great.
Okay. Any answer? Then we have 5 minutes left for the final discussion. What was the result, Anka?
Again, a little bit the same view on this.
Thank you. Same. That's, so to say, very much but the same the pattern it shows. That economic viability and positive business case comes out as it being very, very important. However, to conclude the discussion on hybrid, in my introduction, I said hybrid is the combination of blue-green, gray water technology and smart. And as this Water Innovation Europe is about a smart water society, I'm asking to the panelists, or to the people speaking about the examples, but would it be helpful if you made your solution more smart, more monitoring and control in there to really steer and control? How smart is it? And would it be helpful to make it even more smarter? Who could respond to that?
I can start that one, Frans.
One at a time. Go ahead.
Okay, yeah. I think this example, or what I showed, this is not smart, but there are quite many technical or engineering issues in that one, or features in that one. So there are many valves which are steered by different sensors and stuff like that. And to be honest, I think that one is too smart in theory, but not sufficiently smart in practice. And I think when we look on these decentralized facilities, we have to find we should not do it smart per se, yeah, just to do it, just because we can. But I think it's very important, especially if we're small decentralized facilities, that we also think about the robustness of the systems.
Sure.
Because the system what we have is not robust enough. There were many failures which were connected to this level of kind of too much technology, too much engineering, too much smartness.
Josh.
Yeah, I think there are a couple of avenues that we can talk about smart being useful for our system and maybe some of the systems of the others. Something that's spoken about is predictive weather adjustments, so that we capture more rain when more rain's coming, and you can balance that with the way that you treat the water in terms of residence times and things like that. And going to the other side is the quality side, which is the systems we install are controlled by a PLC, so that there are pumps and valves that are operated by a computer. And what we're trying to do is use that smart system to come to a point where we understand what a dumb system can look like, or a dumber system. And you can use a lot of analytics to evaluate quality from an empirical level when you have enough systems. And then you can come up with programming that just works, and then you don't have to do that anymore. I think that's the goal for us.
Simplify.
Yeah.
Please be brief, because we have minutes to get to the left. Edouard.
Yes, thank you. I'm not sure we might need smarter solution and more smart solution. Of course, monitoring the quality of the wastewater at the end of the system when the water is released might be interesting to have maybe a daily tracking to check when an issue occurred, to connect it to some thing we did in the workshop, maybe some new products we use. But as we are not dumb, I think we can handle this kind of situation even with a 2-week control or a monthly control as we have now. It's been working since for a decade now. So,
Stefan, one sentence, please. Then.
Yeah, well, I very much agree with Godeka. In the agricultural setting, we see that the users really require very robust and easy to use technology, and so it should not be too difficult.
Well, let me conclude by saying I disagree. Your car has 54 processors at the moment, and so hundreds of monitors in it to control the engine. And nobody knows. But robustness is the answer to this.
My car doesn't have these sensors, but it's a robust one.
It's very robust. But one final point to conclude, that is one of the conclusions of the questionnaire. Question 2B, you said you made this judgment because the solution has the least barriers for uptake in policies and legislation. I was surprised by that. So these governance barriers are the most important barriers for introduction. You all agree on that?
Well, what I also mentioned in my presentation is what I see is that you need a certain incentive in many cases, and I think that's so yeah. Sometimes it's barriers, but for water quality, which is not the main interest of, for instance, the farmers, you need that there's a benefit for them to do it. And in that respect, I think a very clear incentive is very important, I think.
The benefit is the importance of the thing to overcome these barriers. You conclude.
Yeah, there should be a reason why people take the time and the money, etc., to install such a thing.
Yeah. I think we have to conclude now, because I know Anka is getting nervous that the next meeting has to start, and she's very busy. I would like to thank you, well, first of all, the audience for their attendance and their questioning. I really appreciated you being here and asking questions. The speakers of today, I'm not going to call the names, that takes time, but thank you for presenting these examples, because leading by example is what you have to do in daily life as well. I think all the examples are worth being demonstrated to a wider audience. And as for hybrid green-gray solutions, our next steps will be that we will continue to try to develop a research agenda to find out better solutions, but also to overcome the governance barriers and to get a wider introduction and better solutions in practice. For the moment, thank you all for helping in preparing this meeting, giving your contribution, attending. Thank you so much, and enjoy the rest of your afternoon. Thank you so much.
Thank you.
And thank you, Anka, for hosting all this.
Thank you, everybody. Thank you. Bye.
Bye-bye.
Thanks. Thank you.